Hi, this is Steve Denenberg. In this video, we will continue our discussion of the physics of springs and simple harmonic motion. Next, we're going to talk about the amplitude of spring motion. Here we have our spring attached to the mass. If you grab that mass and you pull it out a little bit, it'll oscillate back and forth a little bit. If you pull it out a certain distance, when you let go, it'll move back to equilibrium position, and then the spring will compress the same distance away from equilibrium position that you pulled it out originally. If you pull the mass out farther and let go, then the spring will come back to equilibrium position and it'll compress that same distance. And then come back to the equilibrium position, and then go back out as far as you pulled it, as long as there's no friction to take energy away from the system. So here's a question. Let's say we pull the mass out a little bit, and it rocks back and forth a little bit, back and forth. And we measure the frequency of oscillation. How many times per second does it complete one complete cycle? And have we talked about what one complete cycle means? Pardon me if I'm repeating myself, but if we pull the mass out to here and let go, it's going to go in until it gets all the way compressed, and it's going to come out back to the other extreme. And that is one complete cycle. And the amplitude of this motion, if here's the mass at equilibrium position, is the distance that it traveled in each extreme from the equilibrium position. You can see that here I'm using the right edge of the mass to define where I am. But so this distance here is the amplitude of the motion. But so let's go back to our question. You pull the spring out a little bit and it rocks back and forth a little bit with a certain frequency. Well, what happens if we start out by pulling the mass way out and asking it to go back and forth a much bigger distance? The scale of this drawing won't allow it, but we increase the amplitude greatly, the same mass, the same spring. What will happen to the frequency with this bigger amplitude? Well, let's think about it for a minute. If you pull the mass out farther, it's got farther to go all the way back to equilibrium and to compressed and then back and all the way out to that extreme again, one cycle. So that would suggest it's going to take more time for one cycle. But on the other hand, you pull it out farther, the original displacement is greater. If x is greater, there's a greater force on the mass, and force equals mass times acceleration, and it's the same mass, so the acceleration at the extreme point is going to be higher. Maybe that'll make up for it. What's the answer? There is an answer. We previously determined that the frequency equals 1 over 2 pi times the square root of the spring constant divided by the mass. Do you see amplitude in that equation anywhere? It's not there. So a particular spring and a particular mass will oscillate back and forth with the same frequency, whether it's a small amplitude oscillation or whether it's a large amplitude oscillation, the same exact frequency. Now next, let's talk about gravity. Here is our horizontally oriented mass on the spring, and it's sitting at rest in its equilibrium position. The spring has this length L. Force equals negative kx. It's in an equilibrium position, so the displacement from equilibrium position is 0. The force on the mass is 0. There's no net force on the mass, so it's not moving. Everything is at rest. What happens when we move this vertically? and we hang the spring from the ceiling. Well, let's draw it. Here's our ceiling, and we're going to pluck the same spring off of the diagram above and just sit it there. The spring is this long. This is its non-extended and non-compressed length. It's going to be the same length because it doesn't have any mass. Why doesn't it have mass? Because we're calling for all of these computations for the spring to be an ideal spring. And an ideal spring has no mass, and there's no friction involved in its expansion and compression. And it's also a linear spring. Aha! What does linear spring mean? Well, let's go back to our force displacement chart. So here's our chart that shows that for a given displacement away from equilibrium position, there's going to be a certain force. The restoring force is greater, the greater the displacement from equilibrium position. So the slope of this is K, the spring constant. Well, this is a line. It's linear. That's what they mean. What would be a nonlinear spring? Well, imagine a loosey-goosey spring that you stretch it out and you stretch it out. Eventually it breaks. And so if you just keep increasing X more and more and more, the force available is going to stop growing and it's going to curve out like that. But for our purposes, we're talking about the linear portion of this diagram. That's our ideal spring. So anyway, we have our spring, and now we hang the mass on it. And look what happens. The spring stretches out to here. Why did it do that? Well, because whereas up here, there's no force on the mass itself, here we have the force of gravity pulling down on the mass with the force of mg. Well, how far did the spring stretch when we hung the mass on it? Well, it stretched this far, d, and it stretched far enough that the spring's restoring force just balances the force of gravity. That's if there is no motion now. The mass is not bobbing up and down. This is our equilibrium rest position. And how far is d? Well, if the spring constant is really big, it didn't have to stretch very far to offset the force of gravity. We say that Kd equals mg, because the force, restoring force, is the spring constant times the displacement away from equilibrium. And so d equals mg over k. And if you work it out, this is in meters, and this will turn out to be meters as well. So what we do is we set this new position, the rest position. This is our equilibrium position. And now you can pull the mass down, and it will bob up and down with some amplitude. And the frequency is still going to be 1 over 2 pi times the square root of k over m, just like on a horizontally oriented mass and spring. It's just this is our equilibrium position, the place that it drops to and sits with no motion in the gravitational field. Easy peasy. Now next we're going to talk about potential energy and springs. Here is our mass on a spring, and this spring has been compressed. We've pushed the mass to the left, and we've put a little blocker in there so the mass can't travel back to the right. You can imagine that this spring has some potential energy stored in it, because we know if we release the blocker, the force from the spring, the restoring force, will push the mass out to the right and turn that potential energy into kinetic energy. Indeed, if this spring is not completely attached to the mass here, after the spring extends out to its equilibrium position and at that point starts to slow down, the mass will continue out beyond the spring with a certain velocity and a certain kinetic energy. And the kinetic energy it has here will be the same as the potential energy stored in the spring here. This is very similar to the situation of a block on the edge of a cliff. It has potential energy by virtue of its height above the ground in a gravitational field roll the block off the edge, and the force of gravity is going to turn that potential energy into kinetic energy. How do we quantify how much potential energy we have? Well, the potential energy of the block up here is equal to the work that was done on the block in elevating it to that point against gravity. Remember, work equals force times distance, as long as the force is in the same direction as the displacement. We're leaving the cosine theta out of here. But so we're working against the force of gravity, and we're traveling a certain distance. And the work done on the mass bringing it up to that height equals mgh, which equals the potential energy of the mass at that position. Same thing over here. If you take a mass on the edge of a spring, as you're pushing it in, the distance you travel times the force of the spring at the time of that particular push equals work you are putting into the system and can get out later by converting the potential energy in the spring to kinetic energy. As you press the mass in farther and farther, the restoring force of the spring gets larger and larger, and the work to compress it another centimeter gets more and more. Whereas in the gravitational field, every foot you raise it costs you the same amount of work and gains you the same amount of potential energy. Well, let's see if we can figure out how much work it takes to compress that mass, and that'll tell us exactly how much potential energy we have in the spring to liberate for some other use later. Work equals force times distance. And then, just as, once again, to find the area of a rectangle, we take its height times its width to get the area. That equals height times width, and it's the area in our height-width chart. Similarly, if we want force times distance, we draw our force-distance chart, and we compute the area. Well, the force-distance chart for a spring has a slope of k. The greater the displacement from equilibrium position, the greater the force required to hold it there. And with this force varying along here, the work done, force times distance, is the area under the force distance chart. So we're going to take this mass on the spring and we're going to compress it a distance x. That's how far we're pushing it in. And this is the distance we're pushing it in. And the work that we did is the area under the force distance chart. And please, let's make sure that's obvious. Force times distance. If the spring, and it's not, but if the spring had the same force regardless of the compression, then the work done, which is force times distance, would be force times distance, the area under the chart. Well, we have a situation that the force varies with distance. But that's okay. The answer to the question of how much work is done is still the area under the chart. So let's go back here. Here's our triangle. We compressed it x. So the base of this triangle is x. And the force that is the height of the triangle equals what? Kx. So the area of a triangle equals 1/2 times the base times the height. The base is x. The height is kx. So that's 1/2 times x times kx, and that's 1/2 kx squared. And that's the area under the force displacement chart. And so that's the work done. And that's also the potential energy stored in a spring of spring constant K that has been compressed x distance from its equilibrium position. So let's work a problem. Here's our mass. It's being held with a little blocker. It's been compressed from its equilibrium position a distance x naught. And we're going to release the blocker. The spring is going to expand, pushing on the mass. And the mass is going to travel out to the right on this friction-free surface with a certain velocity, v sub naught. And we want to find what v sub naught is. And we're going to do it with an energy approach. Now, you may remember from the videos on energy and work that it's crucial that you start every problem that has to do with energy with this equation. The energy initial equals the energy final. Now, that gets modified slightly if there are non-conservative forces involved, like friction, to steal energy away from the final energy. But here there's no friction, there's no non-conservative forces. So we always write this equation. And then we always write the next equation. The potential energy initial plus the kinetic energy initial equals the potential energy final plus the kinetic energy final. Writing these two will keep you out of trouble in a lot of problems. Things have to be done step by step. So the initial potential energy is 1/2 k x sub naught squared. The initial kinetic energy is 0 because the block isn't moving. The final potential energy is 0 because the spring is no longer compressed. It's resting at its equilibrium position. And the final kinetic energy is 1/2 m v sub naught squared. Understanding this pretty much finished the whole problem for us. 1/2 k x sub naught squared equals 1/2 m v sub naught squared. K x sub naught squared equals m v sub naught squared. I'm going to switch sides since we're looking for v sub naught. M v sub naught squared equals k x sub naught squared. V sub naught squared equals k over m x sub naught squared. And v sub naught equals the square root of k over m, there's that square root again, times x sub naught. And there's our answer. And as you should do many times when you get an answer, look at it and see if you think it makes sense. The velocity after expansion of the spring is this. Well, let's see. If the spring constant is very big, then the velocity will be greater for a given distance of compression. Well, sure, a stronger spring is harder to compress that distance and will turn into more kinetic energy. And if the mass is large, mass is in the denominator, the final velocity will be smaller because the expansion of the spring pushing on a larger mass will cause less acceleration and less final velocity. Okay, makes sense. And let's do another problem to make sure we've got it, that we know how to work with the equations. A spring of strength K is compressed a distance x sub naught, so it's holding potential energy. The spring is released, the mass is thrown out, and the mass heads out this way at a velocity v sub naught. Fine. Now what we're going to do is we're going to triple the spring constant. We're going to triple the strength of the spring. And now, what is the new speed of the mass? with the stronger spring in terms of its old velocity? Is its velocity going to double, triple, times 9? This is a very hard problem to do if you're in the habit of doing 2 or 3 steps at a time writing your equations, and it's a very simple problem to do if you only do 1 step at a time and you write everything down. So, with the original spring constant, we'll call it k sub naught, we had from just above the final velocity, v sub naught, equals the square root of k sub naught over m sub naught, and m is not going to change, times x sub naught. And x sub naught is not going to change. So now we're going to run this again with the new spring constant. So we're going to say the new velocity from the new spring constant equals the square root of the new spring constant divided by the new mass, but the mass is the same, so I'll call it m sub naught, times the new displacement, but that's the same too, so we'll call that x sub naught. But now we know that the new spring constant is 3 times the old spring constant, because that was the point of the problem. So let's write that in. The new velocity equals the square root of 3 times the old spring constant over the old mass times the old displacement. So new velocity equals the square root of 3 times the square root of k sub naught over m sub naught times x sub naught. And this right here is the old velocity. And this right here is the square root of 3. So the new velocity is the square root of 3 times the old velocity. And you should be this careful with all of your calculations, and you can do any kind of a problem. Let's do one more really quickly just to show you. We're going to say that we did this situation with a certain mass, a certain spring constant, and now we're going to do it again, but we're going to increase the spring constant by a factor of 5, and we're going to double the displacement. Very easy. We have the original situation, v sub naught equals the square root of k sub naught over m sub naught times x sub naught, and our new velocity equals the square root of k new divided by m new times new displacement. So the new velocity equals the square root k sub new is going to be 5 times the old spring constant. M stayed the same, and the new displacement is 2 times the old displacement. Did we get that right? 5 times the old spring constant and 2 times the old displacement. Now just do the math. V new equals square root of 5 times the square root of k sub naught over m sub naught times x sub naught times 2, and all that equals 2 square roots of 5 times v sub naught. So the new velocity is 2 times the square root of 5 times the old velocity. Once again, easy if you don't panic and just write it out. In the next, the third video of this series on springs and simple harmonic motion, we'll discuss another equation from the page of formulas provided for the AP exam. Very exciting. Thank you.